Good. Yeah, it's good to go.
Okay, great. Right. So the kind of general topic of well, much of my research is this kind of basic question about the power of quantum computers. And so, you probably are aware that there are some things that we think we can, some computational problems that we think we can solve faster using quantum computers by somehow designing algorithms that take advantage of things like superposition and interference, phenomena in the quantum world that allow us to solve some problems dramatically faster than we would be able to if we just used computers built out of classical stuff. And there's a variety of quantum algorithms that have been discovered now. Actually quite a lot. Some of these are algorithms for problems where we think we can get an exponential or at least a super polynomial speed up over what we can do. Classically, the most famous example of such a thing is the factoring algorithm discovered by Shor in the mid-90s. And there are other kinds of problems for which we have maybe more modest speed up, but there are many such problems that we can get this kind of speed up with quantum computers. The kind of maybe best known example of such an algorithm is the algorithm for unstructured search, which will feature various times in this talk. This is due to Love Grover, also from the mid-1990s. But there are a lot of algorithms that have been developed for various kinds of problems having to do with graphs or algebraic structures or geometry. Many kinds of problems for which we can get these kinds of polynomial quantum speedups. So the kind of basic question that we're interested in this kind of area of quantum algorithms is just understanding what are the problems for which we can get these speedups and how much speed up can we get. And so that's the kind of like setting for kind of everything that we're going to talk about today. Okay, so but the other kind of thing that we I guess would like to understand that would maybe help us address this question of what we can do faster with quantum computers than classical ones is to develop tools that we can use to design design quantum algorithms. So the toolbox is kind of ever growing. It's maybe not that full, but now we have a bunch of different ways we can potentially try to develop quantum algorithms. And the more tools that we have at our disposal, the kind of better off we are in terms of being able to find more and more varied speedups. So, there are tools like, for example, Fourier sampling, which is somehow the kind of workhorse of Shor's factoring algorithm. There are ideas like Grover's search algorithm and kind of quantum walks on graphs that have been applied to many, many different kinds of problems. There are some other techniques that are listed here, not all of which I'll go through. But the main thing that I want to talk about today is kind of a new tool that we have developed, a sort of new way of thinking about how you can design quantum algorithms. And I'll show you how we've applied it to a few problems. And I hope that it will be useful for more things in the future. I would like it to be kind of a generally useful tool for designing quantum algorithms. Okay, so this tool that I want to talk about is called divide and conquer. And actually, this is a very well-known technique. Like if you've taken a course on algorithms, you've surely heard about this. It's a very basic kind of paradigm for designing algorithms that goes back a long way. So the basic strategy is kind of as follows. So we divide our problems somehow into subproblems. Then we solve those subproblems. And that usually the solution of those subproblems is done recursively, right? So the way you solve those subproblems is by applying the algorithm that I'm now describing until you bottom out with some kind of small enough instance that you can just solve it by brute force. But anyway, then once you have the solutions of those subproblems, you do some additional computation to combine the solutions that you found in order to solve the overall problem. And hopefully you don't have to do too much additional work to combine the solutions of those subproblems to get the solution of the full problem. Okay, so probably the classic example of this in classical algorithm design is for the problem of sorting using what's called the merge sort algorithm. So if you've taken a class on kind of classical algorithms, surely you've seen this, but just to kind of set the stage, let me sort of describe this because it's going to be sort of a prototype for the kind of thing we're going to do in quantum algorithms. Okay, so in merge sort, we've got some lists that we want to sort. And the first thing we're going to do is we're going to break that list into sublists. So in this algorithm, and actually in many applications of divide and conquer, we just divide the input into two pieces. So that's what we're going to do. We're going to divide the list into a left half and a right half. And then what we're going to do is we're going to sort the left and the right halves. We do that recursively. So we're going to do that by applying this algorithm again, by dividing, subdividing those lists in half, et cetera, until we sort of bottom out till we have a list that's just sorted because it's only one element. But imagine we do that. We go through all that recursion. We sort the two lists, right? So we started with these two unsorted lists, then we sort them. So they're individually sorted. Now what we would like to do is we would like to take those two sorted lists and we would like to produce a single list with all of the elements in sorted order. And the point is that this is now much easier to do than if you were just given the original list, because these two halves are sorted. And so you can just make one pass through the list, kind of figuring out which is the smaller element, right? This, you kind of have pointers at the beginnings of the lists. And since this element is smaller than this one, you take this one first, then you take this one, then you take this one, et cetera. So you just have to make one linear sweep through these lists to be able to merge them. Right? That's the kind of the merge of the merge sort. So you can merge those two halves in linear time. And so that gives you a kind of a recurrence for the cost of solving this problem, right? So the cost C of n of sorting this list of length n obeys this recurrence, where what you do is you solve two subproblems of half the size, and then you do a linear amount of extra work. And then you can solve this recurrence using the, I guess the initial condition is that like C of 1 is 1. And what you find is that the kind of the cost of sorting the list of length n goes like n log n. So this is the complexity of merge sort. And so for this to be the case, it was crucial that, this extra work was not too large, that it was only linear. And because of that, you can solve this recurrence, for example, using this thing called the master theorem, and you get this result for the complexity. Okay, so we would like to take this idea and somehow make it quantum mechanical. That's the idea. We want to somehow give quantum algorithms that somehow get quantum speedups by doing something like this, divide and conquer strategy. And I want to sort of explain how that might work using a really simple example. That's a problem that we already know how to solve without using divide and conquer, but sort of maybe will help us to think about how we would approach this. So this very simple problem is going to be actually basically this problem that Grover's algorithm solves, which is the problem of computing the logical OR of n bits. Right? We want to compute, whether there's a 1 in this string of n bits. Okay, so here's a natural way we could divide and conquer to try to solve that problem. We divide up the n bits into the left half of the bits and the right half of the bits, and then we compute the OR of the left half and the OR of the right half recursively. And then we take the OR of just those two bits, right? And that we can do really easily because it's just a single OR operation. Okay, so if we did this classically, now there's really no extra work. If we think about the queries that we need to make, right? If we do this in query complexity, where we ask how many of these bits do we need to query to get the answer, we don't need to do any extra work in the merge. We just compute the OR of two things that we explicitly know. So then the classical query complexity of solving this problem is at most twice the cost of computing the logical OR of the left half and the logical OR of the right half. And of course, if you solve that recurrence, you get that the cost is at most n. Of course, this is, this is just the trivial algorithm of querying everything, kind of done in this kind of complicated way. But it does certainly get you the OR in that cost. Okay, but now what would happen quantum mechanically? Well, what you might like to sort of imagine, perhaps you could do quantum mechanically, is divide the problem up in the same way into a left half and a right half. But suppose that somehow instead of a 2 here, you had the square root of 2, because we know that quantum mechanically we can get a square root speed up for computing the OR function. So if we sort of could do that at the level of like just computing the OR of this thing and this thing, you might think maybe there should be a square root of 2 here instead of a 2 here. This doesn't really make sense, which is why I put a question mark over this inequality. But suppose you put a square root of 2 there and you just run with it, right? Well, then if you would solve the recurrence, you would get sort of the right answer, right? You would get this, you would get the result that the cost is like the square root of n. But can we sort of like justify that, right? This is somehow, I mean, it's a little bit crazy what I just said, because, for many reasons. So the quantum query complexity of OR is only like big O of the square root of n. It's not actually equal to the square root of n. So, why would we just put the number square root of 2 here, right? For this to be the case, it's really important that this is not just like, some constant times square root of 2. It really has to be square root of 2 to get this square root speed up, right? This recurrence is very sensitive to what particular value you put there. Also, when you do this, you compute the OR with bounded error. So like you would have to worry about the growth of that error when you apply this recursion. That's sort of another problem. And also like the interpretation of this too was like it was the number of subproblems you had to solve. But the square root of 2 is not an integer. So I mean, like, what could the interpretation of this possibly be? There's no such thing as solving square root of 2 subproblems. So it kind of seems a little bit crazy. But what we're going to see is that we can actually give a framework where something like this really does happen. And so if you know, if you've heard of the quantum adversary method or you know how it works, that's going to be an ingredient. And so from that, maybe you can already see how we could perhaps make sense of something like having the square root of 2 here, although we're going to do something that's more than just sort of applying the quantum adversary method in a way that I'll explain coming up. Okay. All right, so now, what is this kind of general sort of like framework going to look like for doing, divide and conquer in this quantum world? So, kind of in general, the general sort of form of a, or at least the typical form of a kind of recurrence relation that you would get in a classical divide and conquer algorithm is that, you have your instance of size n, you divide it into A instances of size n over B. They could be maybe overlapping. That's why maybe, A doesn't necessarily have to equal B. And then you solve these A instances of size n over B, and then you do some auxiliary work to kind of put together the solutions of the subproblems, right? So what we would like is to have something, like this, where somehow if we would do this on a quantum computer, we would get to put a square root on the A. And also, so that's one way we can get some kind of, oh, and I'm sorry, this should be CQ. So yeah, we would like to sort of get this advantage of having a square root of A instead of just A. And also, the other thing that we can maybe take advantage of is when we have to do some auxiliary work to combine the solutions of the subproblems, we can use quantum algorithms, right? So like maybe we could take advantage of the ability to use Grover's algorithm to do something, faster than we would be able to do classically, so that we can reduce this. So that's kind of the idea of the strategy, and we're going to sort of see how we can how we can kind of make sense of this through the quantum adversary method, and then how we can apply this to speed up the solutions of some problems. Okay, so all of the kind of speed ups that I'm going to talk about are going to be in the context of query complexity, which I guess I already alluded to, where we're not going to count all of the elementary operations, but we're just going to count queries to a black box. And this is a kind of a useful framework for kind of investigating the power of quantum computers. So the main idea is that we've got some input that's not given to us explicitly, but it's given to us by a black box. And we're just going to count the number of queries that we have to make to that black box to learn, some property of the input. So that's kind of the setting. We're not going to focus on elementary operations, but really just on these queries. And we can think about this notion of query complexity in a variety of different models. We can talk about classical algorithms that definitely have to succeed. We can talk about randomized algorithms that just have to succeed with a high enough probability, like they have a bounded failure probability. Or we could talk about quantum algorithms that can make quantum queries, querying the data in superposition. And again, these are typically going to be bounded error algorithms. And so we're interested in, in particular, in showing cases where we can get a significantly lower quantum query complexity than the classical query complexity, usually where we would like to get an improvement relative to the randomized query complexity. So, a very simple example of this is this problem of computing the OR of n bits, where, classically with either deterministic or randomized algorithms, you need a linear number of queries, but quantumly you can get by with the square root of n. Okay, so that's going to be the kind of setting that we're going to be interested in. We're going to try to do divide and conquer on, various kind of problems in this black box model. Okay, and I mentioned briefly the quantum adversary method. So this is going to be an important tool in our framework. The quantum adversary method is something that was originally developed as a way of lower bounding quantum query complexity, of showing that you need to make a lot of queries to solve some problem. But then it turned out that a particular version of this problem that was a bit of a generalization of the adversary method that was originally proposed, this kind of generalized quantum adversary method, turns out to be not just a lower bound, but actually up to constant factors, also an upper bound. So in other words, it gives you lower bounds that are always tight. And so this, you can think about this as a tool actually for coming up with algorithms, because it gives you really sort of always the right answer. So, imagine you've got some function you would like to compute on some black box input that comes from this set S, right? So S is like a string of n characters over some alphabet sigma. The model is that you have black box access to those characters. So you can ask for the ith character of that string, and the black box will tell you what is the ith character. And then your goal is to compute some function f, like f could be the OR function, for example, or it could be some other function of that input that sort of tells you about some property of this input string that comes from the set S. Okay, so the adversary method, sort of the details of it are not so important, but it's a kind of spectral quantity that you can write down. It's actually captured by a kind of optimization problem called a semi-definite program, and that's kind of behind the fact that it's actually both a lower and an upper bound on quantum query complexity. So there's some kind of way of sort of cooking up a matrix that has to satisfy some conditions that depend on the function, and then there's some sort of optimization problem over such matrices whose value is this thing called the adversary quantity of the function. And yeah, let me not sort of really get into the definition because it's not going to be so important for us. Really, the fact that we're going to use, or one of the main facts that we're going to use, is that this adversary quantity really captures the quantum query complexity. So the quantum query complexity, the bounded error quantum query complexity of some query problem, captured by some function f, is really like big theta of this adversary quantity. Okay, the other main property that we're going to use is sort of nice composition properties of the adversary quantity. So it turns out that this adversary quantity behaves well with respect to function composition. And this is, basically what's going to allow us to get this square root of 2. Okay, so in our quantum divide and conquer algorithms, we're going to use, in the examples that I show you, we're going to use two different kinds of composition. One of them is what we might call OR composition. So imagine we have some function g that we're interested in computing, and we can think of g as the logical OR of two other functions on two parts of the inputs. They could be overlapping parts of the inputs. There could be correlations even between x and y. That's sort of not important, but here g is, let's say, the logical OR of these two functions. Then you can show that the adversary quantity of the composed function, the adversary function of the OR of f1 and f2, is at most the square of that is at most the sum of the squares of the adversary quantities of the individual functions. So you can think about this, for example, like if this is just the OR of 2 bits, these are just 2 bits x and y, then I guess the problem of just you have query access to that bit, and the goal of the query problem is to produce that bit. The adversary quantity for that function is just going to be 1, and correspondingly the adversary quantity for the OR function on 2 bits is just going to be the square root of 2. So this is kind of the sense in which we can imagine that we have that square root of 2 in our divide and conquer recurrences. And this idea actually generalizes to kind of in a nice way to arbitrary and/or formulas, arbitrary formulas that you build up out of ands and ors of various input functions. Okay, the other composition rule we're going to use is one that it's pretty straightforward, but we actually came up with it for this project, which is what we call switch case composition. So the idea here is that you want to compute some function at h, and that function is some function g chosen from some set of possible functions g that are indexed by some function f. That's also a function of the input that you have to compute. And so the cost of, in terms of this adversary quantity of computing this function h, is at most the adversary quantity of the function f that you have to compute to figure out which function g that you want to compute, plus the largest of the adversary quantities of any of the functions g that you're going to compute. Right. So I call this switch case because it's like you evaluate this function f to figure out which case you're in, right? Which of the g's you want to compute. And then once you know that the index is f of x, you go and compute the corresponding g corresponding to that on your input, right? So basically you have to sort of, it's kind of intuitive, like you have to sum up the cost of, the cost of computing the function f with the sort of largest of the costs of computing any of the g's. And it's going to be important for us, there are going to be places in our analysis where kind of constants really matter to get recurrences to be right. Here, there's maybe some this is loose up to some constant, but this one really just is the adversary quantity of g sub s that matters here, and that's sort of like important for getting the kinds of speedups that we want to show. Okay, so using this kind of adversary composition principle, we can have sort of like divide and conquer algorithms that sort of like put together the work involved in solving subproblems and the work involved in kind of stitching together the results of those subproblems. And that's what we're going to see in this kind of quantum divide and conquer framework. So if we have some function that we can compute as some and/or formula of a bunch of other functions, and then we have some other auxiliary function that also goes into figuring out how to compute the value from this, the result of this and/or formula, then we can compute the square of the adversary quantity, or we can bound the square of the adversary quantity of this function we're trying to compute in this way, that it's at most the sum of the squares of the adversary quantities of these FIs, and it's also big O of the quantum query complexity of this auxiliary work. And similarly, we can give a sort of divide and conquer sort of approach that involves this switch case, where somehow we have to do whatever is the work involved in evaluating whatever is the largest of these functions G sub s, and then we have another term which is like big O of the quantum query complexity of this auxiliary function. So here we've kind of gone back, we've done this thing of going back and forth between the adversary quantity and the quantum query complexity. Okay, so yeah, I want to stress at this point that we're using adversary composition in this work, but we're not just using adversary composition, right? We have terms in these expressions that kind of involve the quantum query complexity, and this is, I would say, kind of the power of this framework, that somehow we can think about applying adversary composition to combine solutions of subproblems, but we can also, for parts of the work that we're doing, just use quantum algorithms. So for sort of the parts of the computation where we don't care about what the overall constant is, because it's not going to affect the scaling of the recurrence, we're free to just think about designing quantum algorithms and not worry about what the constants in them are. But for sort of certain key parts where it's important that we get, exactly a square root of 2, let's say, we can kind of zoom in and make sure that we get that. And that's what allows us to get a quantum speedup. And we'll see this a little bit more explicitly when we do some examples. Okay, and I also want to mention that, these are kind of two strategies that we've used, but there are other kinds of adversary composition principles that are known that would, possibly allow you to apply this kind of a framework to other sorts of problems. So I think there's a lot of potential for sort of extending this tool and using it in other ways, maybe to get other kinds of quantum speedups besides the examples that I'm going to tell you about next. Okay, so that's kind of the high-level overview of the framework. And what I would like to do now is tell you about just a few applications. So in our paper, we have kind of 4 applications. I'm going to just tell you about 3 of them here in this talk. But here's what these applications are. So first of all, we sort of reprove the quantum query complexity of some problems for which nearly optimal upper bounds are already known, but we give sort of simpler analysis and a sort of slight improvement of those upper bounds. And so there are 2 such problems. One of them has to do with recognizing regular languages. So there's this very nice paper by Aronson, Greer, and Schaefer where they gave this quantum query complexity trichotomy for regular languages, showing that this quantum query complexity problem of recognizing a regular language kind of always has one of 3 possible quantum query complexities. And one of the kind of key results inside this paper was this particular language recognition problem of figuring out over this alphabet with 3 symbols whether some string has something that looks like this. So this regular expression means a 2 followed by any number of zeros followed by a 2, right? So you've got some string and you want to know, does it have this sitting inside it somewhere? And so we give a quantum algorithm for this problem that is, the log factors are slightly tighter, and using our framework, it's pretty easy to see why you can do this in like square root of n, if the length of the string is n, in like square root of n quantum queries. We also have some results on these string minimality problems where you have, you're given some input string and you want to find in various senses a kind of a component of that string which is minimal, and there's different kinds of problems like this that are considered in this paper by Akmal and Jin. I'm actually not going to get into the details of this because it's not a new application of our framework, and I guess would take a little bit of time to kind of get into the details. But then we have also 2 examples that we look at that are kind of problems for which we give the first non-trivial quantum algorithms. We're getting kind of polynomial speedup over the over classical algorithms, but also over kind of the obvious thing to do with a quantum algorithm for these problems. And these are the following two problems. So the first one is we're given some string and we want to know, does it have an increasing subsequence of length k? So this is a kind of a variant of this longest increasing subsequence problem, which is a very widely studied problem. If you've taken a course on algorithms, you've maybe been asked to come up with an algorithm for this problem. So we show how to give an optimal or essentially optimal algorithm for this problem. And we also consider a similar kind of variant of the longest common subsequence problem, where you've got two strings and you want to know what's the longest subsequence that they share in common. But again, we consider a version of this problem parameterized by k, and we want to know, do these two strings have a common subsequence of length at least k? And we give a essentially optimal algorithm also for this problem for any constant k. Okay, so these are the applications that we know so far. I'm sort of hopeful that there will be more applications of this framework, but this is kind of the state of the art. So what I would like to do for the rest of the talk is just go through some of the ideas that go into applying the framework to these problems. Okay, so let's start with this problem having to do with regular languages. It's probably the simplest of these problems, and so it's maybe a good one to start with. Okay, so again, the problem is this. So we're given some alphabet. The alphabet is just, let's say 0, 1, 2. And then we're given a string over that alphabet, an in-character string over that alphabet. And we want to know, does that string contain this substring that goes, 2 and then some number of zeros and then a 2. Okay. So that's a regular language, and we want to know if X is like an element of that regular language. Okay, so how can we solve this using divide and conquer? Well, there's a pretty natural way of doing it. So the string is going to contain a 2 followed by some number of zeros followed by a 2 if that object is either on the left part of the string. So X left is going to be the left, the first n over 2 characters of the string. So if it's there, or if it's on the right, or if it crosses from the left into the right, right? So crossing from the left into the right would mean that the string on the left ends with a 2 followed by some number of zeros, and the string on the right starts with some number of zeros followed by a 2, right? Okay, so now how can we sort of solve this? What is sort of the cost of doing this? Well, these subproblems we're just going to solve recursively, right? But this is like the kind of extra work that we might have to do. So we want to know what is the cost of doing that. But it turns out that this is something you can do pretty straightforwardly with quantum algorithms that take big O square root of n time, right? You can do that because basically you can use Grover search. You can sort of like search for the last 2 in the left part of the string and the first 2 in the right part of the string. And then you can use another Grover search to see if it's really the case that it's a string of zeros connecting those things, right? That would have to be the case for you to be sort of in this third case where the 2 followed by the zeros followed by the 2 is kind of bridging the left half and the right half. Okay, so this is like, the kind of the classic setup for our quantum divide and conquer. Now we have a recurrence for the adversary quantity for this problem that says that the square of that adversary quantity is at most 2 times the square of the adversary quantity for the problem of half the size. So like if we would take square roots, right, then this would give us the square root of 2 here, plus the work that we have to do for the this case highlighted here in yellow, squared, right? So the cost for that is like the square root of n, and then things are kind of added in quadrature here, so we have this thing squared. And the solution of this recurrence is just, with I guess a of 1 being like a constant, is like the square root of n log n, right? And it turns out that this is sort of an optimal algorithm for this, for an optimal complexity for this problem. This is really sort of like the right answer, at least up to this like square root of log n factor, right? So this kind of, improves the log factors, which maybe even aren't worked out explicitly, but I think it improves what they would be if you would work them out explicitly in this paper, and also has really quite a simple, conceptually simple proof of the complexity. And I think this sort of illustrates the potential power of this method, that it kind of really lets you kind of think classically about how to solve a problem, plug in some kind of basic quantum ideas, and get potentially a quantum algorithm that has a lower query complexity than you would have in the classical case. Okay, great. So so that's the kind of simplest example. Let me next do one which is a little bit more involved, which is the increasing subsequence problem. So by a subsequence of a string, what I mean is a subset of the characters that you take in order. So you don't change the order of these characters, but you don't have to they don't have to be consecutive, right? So if they have to be consecutive, that's what's called a substring. But this is not that. You're allowed to just sort of extract some pieces of the string. And now there's this kind of classic problem in classical algorithms, the longest increasing subsequence problem, which just says you're given a string. This alphabet has to be sort of ordered. So this notion of increasing makes sense. And then the goal is to find a longest increasing subsequence of that input string. So for example, if I have this sequence, 8, 6, 7, 5, 3, 0, 9, then the longest increasing subsequence of that is 6, 7, 9. In this case, it's actually unique. It doesn't have to be unique in general. That's why I just said a longest increasing subsequence. I think in this case, it's actually unique. Okay, so it'd be nice to think about what's the quantum query complexity of this problem, but actually that's not such an interesting question, because the answer is just trivial. That you can show pretty easily that the quantum query complexity of this longest increasing subsequence problem is just linear. You just have to know the whole string. So classically, that's the case too, but even quantumly, there's no quantum speedup. You just have to make a linear number of queries in general to find a longest increasing subsequence. So that makes the problem not, it makes it so there's not really much interesting to do for the kind of vanilla version of the problem. But if you introduce this parameter k, then something kind of interesting happens, and that's what we're going to work on. So now what we're going to do is we're going to say, imagine there's some value k, and we want to know, is there an increasing subsequence of length k? Or I guess I could say at least k, because if there's one of length k, of length longer than k, then there is one of length k. Right? So so this is the k increasing subsequence problem. Is there an increasing subsequence of x of length equal to k? Okay, so what can we say about this problem? Well, this problem is still hard for classical computers, right? So I guess one increasing subsequence is trivial because every string has a increasing subsequence of length 1. But already once k equals 2, the query complexity is just maximal. Classically, like even to decide if there's an increasing subsequence of length 2 already takes a linear number of queries. Classically, you can probably easily convince yourself of that. But quantum mechanically, you can get an improvement for that case, because basically, if you want to know if there's an increasing subsequence of length 2, it's enough to find out, like, is there a place in the string where it's increasing? Right? Because if there's an increasing subsequence of length 2, there has to be a place in the string, like it can't be always decreasing. So there has to be a place that you can search for where the sequence actually increases from one spot to the next. And that's exactly the kind of thing you can find using Grover search with a cost like square root of n. Okay, so that's good. But what about larger k? The problem gets harder as k gets bigger. So what can we say when k gets bigger? Well, there's an algorithm due to Mbinus for a problem called k-distinctness that sort of a slight tweak of it can be applied to this problem. And that would give you a quantum query complexity of like n to the k over k plus 1, which is, definitely better than classical, but it becomes very, very close to the classical cost as k gets big, right? If k is 100, then this is like, n to the 99 over 100. It's, it's almost linear, right? So, yeah, we want to know sort of like, what's the truth? Can we do better than this? Can we somehow give an algorithm that has a query complexity which is less than this? And so we show that in fact this is the case. You can get basically square root of n up to log factors for any constant k. So let me now sort of explain more or less how that works. So right, so for what we show is specifically this: for any fixed k, the quantum query complexity of this k increasing subsequence problem is like square root of n times some power of log n, where that power increases with k. And so the way that works is the following. So we're again going to take the string x, and we're going to divide it into a left half and a right half. And what are the ways that the string could contain an increasing subsequence of length k? Well, it could be on the left, it could be entirely within the left half. It could be entirely within the right half, or it could be that sort of part of it is on the left and part of it is on the right, where let's say I of the elements are on the left half and k minus I elements are on the right half. Okay. And now we have to think about the amount of work that you have to do to sort of check this yellow possibility. And the point is just that, if you want to determine this, you can check this by finding like what's the smallest ending value of an increasing subsequence of length I that's entirely on the left, and the largest starting value of an increasing subsequence of length k minus I on the right. And this is something that you can do using the solutions of the increasing subsequence problem kind of as a subroutine, and some binary search kind of stuff. Let me not get into the details, but basically with like big O of log n computations of this problem, so, solving this subproblem, but not for the same value of k, but for smaller values. We're just looking for shorter increasing subsequences. Yeah, putting sort of those ingredients together, we can sort of solve the thing in yellow. And then the recurrence that you get for the adversary quantity when you do this is as follows. So we have to sort of solve the problem on the left and solve the problem on the right. So that's two instances of this instance of half the size. But again, we're adding stuff up in quadrature because it's the adversary quantity. And then we also have this additional work that involves solving these subproblems, logarithmically many of them. And we have to solve these, but they're for increasing subsequence problems of shorter lengths. So the worst case is like where the length is like k minus 1. And if you solve this recurrence, basically, sort of using this as your induction hypothesis, you can sort of show inductively that indeed this is the quantum query complexity of this increasing subsequence problem. Okay, yeah, so that's the first of these kind of new results. Now, I guess the last thing that I was going to tell you about was kind of the maybe the most complicated of the algorithms, which is the one for the common subsequence problem. But how am I on time? Should I try to go through this, or should I mean, I could just skip it?
You have 10 minutes, so I think you can go with it. Yeah.
Okay, so maybe I'll try to give you at least the highlights of how this common subsequence problem works. It's really the most involved application, but yeah, something kind of interesting happens. Okay, good. Okay, so now we have two strings x and y, and we want to find a common subsequence of them that is as long as possible. That's the longest common subsequence problem. So for example, right, the longest quantum subsequence of quantum and algorithm, here I padded quantum with stars just to make them the same length, like in my problem definition. The longest common subsequence of these two strings is ATM. Okay. So that's kind of the problem in general. We want to find the longest common subsequence. It's a kind of a classic problem to give as like a homework exercise in an algorithms course. And we want to know what we can say quantum mechanically. But again, for the full problem, it's just not so interesting quantumly, because the quantum query complexity is just linear. You can sort of convince yourself that you can't get any quantum speed up for the full version of the problem. So again, we're going to sort of parameterize by k, and we're just going to ask, is there a common subsequence of x and y of length k? And we're going to be interested in doing this for general fixed k, where k is just a constant. Okay, so now the classical query complexity of this common subsequence problem is linear even for k equals 1. Yeah, that's already a hard problem. Now, quantum mechanically, if k equals 1, this is basically like this thing called element distinctness. This is a well-studied problem quantum mechanically, and the quantum query complexity is n to the 2/3. If you consider larger k, you can again use this kind of k distinctness algorithm of Abinus, but it gives you a complexity like this that grows again to be close to linear in n if k gets big. And again, the question is, can we do better than this? And so what we're going to do is we're going to improve on this, using this quantum divide and conquer idea. Okay, so what we show is that actually for any constant k, the quantum query complexity is basically like n to the 2/3 up to some log factors. And so here's the kind of surprising thing. So, most of the time when you apply divide and conquer, at least classically, like you just divide into two parts. You could think about dividing into more parts, but there's kind of no reason to do it because it's not going to give you any advantage, and it's just going to make the analysis more complicated. But for this problem, at least the way that we approach it, we get this quantum speedup by dividing the input into 7 parts. And we would not get the improvement if we would divide, or at least we would not get the optimal algorithm if we would divide into only 6 parts. Somehow we have to divide it into enough parts. So here's kind of the basic high-level strategy. We're going to divide the strings into m parts of length n over m. So eventually m is going to be 7, but we can do the analysis for general m. And then we're going to figure out what collisions there are using the element distinctness algorithm, we're going to figure out where there are collisions between some character in one of the parts of X and one of the other parts of Y. So we're going to sort of figure out something about where there are collisions between parts, between these strings at the level of these entire parts, of length n/7. And then there's kind of two cases that we're going to consider. We're going to consider on the one hand what we might call a simple common subsequence, where it lives entirely within one part of X and one part of Y, not necessarily the same part of Y, but some part of X and some part of Y. There's like a common subsequence of length k just between those parts. The kind of key thing to show is that there's kind of only a limited number of such cases to check, to get sort of like good complexity. And then the other possibility is what we call a composite, common subsequence. And that's kind of everything that's not simple, where somehow the way you get the common subsequence is by taking some collisions that occur, from lots of different parts. And the reason that this can sort of be handled, without too much cost is that it's kind of like what we saw in the increasing subsequence problem, that you only have to find, you can solve this by sort of a process that only involves finding common subsequences of shorter length than k. This is basically because they're composite. Yeah, so I mean, maybe in light of the time, maybe I won't try to sort of explain all of the details. We do this thing where we compute this thing that we call a signature, which kind of tells you where there are some collisions between the parts. That's something that we can do using not too many quantum queries. This is kind of like our budget. We have this n to the 2/3. And then we have this decomposition into simple and composite subproblems. And yeah, I mean, essentially we, let me just sort of say quickly that like when we try to find these composite solutions, as I was saying, we only have to solve instances of this JCS problem for smaller values of J. So that's why this cost is going to be something manageable. And then we can also show that somehow we don't have to solve too many of these, sorry, we don't have to consider too many cases to identify the possibility of these simple KCSs because of something to do with the structure of, where those, what subproblems we could possibly have to consider depending on the signature. I think maybe in light of time, I won't try to explain it in more detail than that. But yeah, the complexity analysis, just to sort of show you where this 7 comes from, is that, when we sort of look at, so we have this square root of 2m-1 that has to do with the number of possible, kind of simple solutions that we could have. That's kind of like the number we have, in some sense, square root of 2m-1 subproblems that we have to consider of size n/m. And then we have some other kind of work that scales like n to the 2/3. And we would like sort of this term to dominate, so we only get the n to the 2/3. And then if you look at what happens in the solution of such a recurrence, basically this term will dominate as long as this coefficient is small enough. And this is where the 7 comes from, that somehow you can show that, this coefficient is small enough once you're dividing into 7 subproblems. So yeah, that was a little bit of a surprise and kind of fun. Okay, so let me try to wrap up there. So, we've introduced this framework for developing quantum algorithms by sort of dividing and conquering, very analogous to how one develops divide and conquer algorithms in the classical world, but using the sort of advantage of, kind of faster quantum algorithms for evaluating and/or formulas and sort of combining that with other quantum algorithmic techniques that we can use inside our sort of combination steps to put together the solutions of the subproblems. And we showed how to apply this to a variety of problems, in particular gave these, improved quantum query complexities for these parameterized versions of the increasing subsequence and common subsequence problem. So yeah, let me just conclude by just mentioning some open problems that I think are interesting. We have one of the things that I'm not sure if it came across in my sort of explanations of these problems, but one of the things that's kind of crucial to the way that we've applied this framework is that we kind of work at the level of decision problems. And it would be nice to maybe more naturally do divide and conquer directly on search problems without it and having to do search to decision reductions along the way. So for example, one thing that I think is a nice problem is to try to give a quantum divide and conquer algorithm for the problem of finding the minimum item in a list. So that's something we know how to do in square root of n quantum queries, but we don't really know how to do it in a divide and conquer kind of a way. And I think if we could, it would maybe sort of light the way forward to more general kinds of divide and conquer algorithms. Also, I mentioned that we can, we can think of other combining functions we could use aside from these and/or formulas and this switch case thing that I described. And, are any of those useful for giving quantum speedups for any other kinds of problems? And finally, so, the largest speedups that we had between, quantum and classical query complexity in the examples that I told you about are only quadratic, like, n versus square root of n kinds of quantum speedups. But I think there's no reason in principle why you couldn't get super quadratic speedups, maybe even exponential speedups from this quantum divide and conquer framework. And it would be really interesting to see if you can apply these ideas to get those kinds of, more dramatic quantum speedups. Okay, so I think I probably should stop there, but thanks for your attention, and I'm happy to take any questions.
Yeah. Thank you so much for a very nice talk. We have some time for questions, actually. Maybe I can start off with something. So I guess, like, since you put this on an open problem, like you probably have thought about this, but at least for the new applications that you found, like, could you make that into a search version, or like even for these particular cases, is it not obvious?
Right. So I think for these increasing subsequence and common subsequence problems, I think there are like kind of search to decision reductions where you can somehow use the ability to solve the problem that we solved, not doing sort of divide and conquer, but just, kind of doing some other thing like, using some binary search or something like that to actually find the increasing subsequence of length k when it exists, for example. That actually does not seem to be the case for these like minimal substring problems. So that's kind of, so in this paper by Akmal and Jin, where they show how to solve these problems, they actually do solve directly the search versions of those problems. So while we somehow simplify their analysis for the kind of the decision, version of those problems, actually we don't know how to do that for the search problem, and there isn't this search to decision reduction that sort of, kind of gets it for you as an afterthought. So yeah, that's sort of another reason to want to be able to sort of work directly on search problems.
We have time for a few more questions.
Is there no algorithm for minimum finding using divide and conquer? You can use the merge sort divide and conquer for finding a minimum. Like, can we not think of applying that for minimum finding?
Right. Okay. I guess you're asking, yeah, you're basically asking, why can't you solve this minimum finding problem by divide and conquer? I mean, I think what you're saying makes sense intuitively, but the some of these kind of composition rules that we use for the adversary quantity, some of these things kind of only work, like something has to be Boolean for these composition properties to hold. Yeah, and I guess I guess we actually know that in some sense it somehow can't work in a really straightforward way. So so it is the case that the adversary quantity of the OR of two things is the square root of 2. But you can define this adversary quantity for like the non-Boolean problem of like determining what the minimum is. But if you have consider the problem where you have some big alphabet and you just want to and you have sort of a string of length 2, and you want to know which is the smaller of the two things, is it the first thing or the second thing? The adversary quantity of that is not the square root of 2. It's something larger than the square root of 2. So somehow you can't use that as kind of the base case for your, or the composition rule for your recurrence. So now maybe you could somehow, maybe bottom out when you don't get all the way down to lists of length 2, but, longer lists or something like this, basically, or you're combining things where you're not dividing into 2 parts, but more parts. Yeah, maybe something like this could work, but I mean, we worked on this for a while, and actually we don't know how to do it.
I had another question, actually. So I was wondering if you could comment on the intuition for this like switch case. So like maybe it was in the beginning, but like on one side, you had like something quadratic, and on the other side, you had something linear. What was that right? I'm not even sure. if
Oh, I think there was maybe a typo actually. I think this
okay.
2 actually shouldn't be there.
Oh, I see. Okay.
Yeah,
I see.
I think here where, yeah. I think that shouldn't be there, I think actually that's a typo. I don't think there should be a 2 there.
I see. Okay. Yeah. Thanks. Let's see. Any other questions? Yeah.
I have a possibly stupid question, which is what other sorts of functions enjoy this type of adversary inequality that I'm seeing here?
You mean besides like and or?
Yes.
Yeah, like for example, if you have you want to compute like the majority of 3 bits, then I think the adversary quantity of that is maybe the square root of 3. Yeah, there are other sorts of small functions where, you know, people have worked out what the adversary quantity is of those functions, and sometimes it's, you know, kind of less than the thing that would correspond to just the kind of the brute force classical computation.
I see.
Yeah.
I see. Thank you.
Sure.
Okay. There are no other questions. I think we can finish this. And thanks, Andrew, for a very nice talk. And I hope to see you in person someday.
I hope so too. Yeah, thanks.
Yeah.
Thanks very much.
Right.
Appreciate the
Bye.
questions.
Thank you.